All right, future physics stars, welcome. Today we are going to absolutely master simple AC circuits. This is a huge topic for your WAEC, JAMB, and NECO exams. And trust me, by the end of this, you are going to have all the key ideas and formulas you need to feel totally confident. So let's dive right in. So here's our game plan. First, we'll tackle the absolute basics, the two kinds of current. Then we'll learn to speak the language of AC waves. After that, we'll meet the main players in any circuit, see how they all work together, and then we get to the really cool parts, the magic of resonance. To finish it all off, I'm going to give you a perfect toolkit of formulas to lock it all in. You ready? Let's go. Okay, first things first, we have to talk about the two fundamental ways that electricity flows. Understanding this difference is the key to everything else. And it all starts with a question you've probably had at some point. And you know what? That's a fantastic question. The answer gets right to the heart of what we are talking about today. It all comes down to two totally different ways that electricity moves. So, on one hand, you've got direct current, or DC. Just think of it like a river flowing steadily in one direction. It's consistent, it's predictable. That's the kind of power you get from a battery. But on the other hand, you have alternating current, AC. That's what's coming out of the sockets in your wall. This current is a bit wild. It's constantly changing direction, flowing back and forth. Here in Nigeria, it does that flip 50 times every single second. Now, because AC acts like a wave, we can't just talk about it in simple terms. We need a special vocabulary to describe it properly. And this is where we have to get clear on the difference between peak and RMS values. The first term you need to know is peak value. And honestly, it's exactly what it sounds like. It's the absolute highest voltage or current that the wave hits during its cycle. Just picture the very tip of that wave. That's your peak. Okay, so that raises a really important question, right? If the voltage is constantly swinging from a super high peak all the way down to zero and then to a negative peak, how can we even talk about its real usable power? Well, the answer is this clever little thing called the RMS, or root mean square value. It is such a smart way to figure out the effective power of an AC wave. Basically, it answers the question, what DC voltage would I need to get the same amount of heating power? And here's the most important part for your exams. Anytime you see a voltage on an appliance, or you measure a socket with a multimeter, you are seeing the RMS value. The formula is easy. Just take that peak value and divide it by the square root of 2. Okay, let's put that formula to work. In Nigeria, our wall sockets are rated at 240 volts, right? We all know that. But remember, that's the RMS value. If you flip that formula around to solve for the peak voltage, get this, you get about 339 volts. No joke. So twice in every single cycle, the voltage in your walls is actually hitting almost 340 volts. It really shows you the difference between the effective power we use and the actual peak the circuit has to handle. Okay, so now we get how AC current works. Let's meet the three main characters that we use to control it inside the circuit. First up, we have our old friend, the resistor. It's the simplest of the three. Its job is just to resist current flow, plain and simple. The most important thing to remember is that in a resistor, the voltage wave and the current wave are perfect partners. They are totally in sync, peaking at the same time, hitting zero at the same time. We call this being in phase. Next up, we have the capacitor. Now, it also opposes current, but its opposition has a special name, capacitive reactance. And here's the crucial bit. A capacitor messes with the timing. It actually lets the current wave get out ahead of the voltage wave. So the current hits its peak a quarter of a cycle, that's 90 degrees, before the voltage does. So for a capacitor, you have to remember the current leads the voltage. And our third player is the inductor. You can think of an inductor as being kind of stubborn. Its whole deal is that it hates change. This opposition to change is called inductive reactance. And it does the exact opposite of a capacitor. It holds the current back, which lets the voltage get ahead. So with an inductor, the voltage wave hits its peak 90 degrees before the current wave. In this case, the voltage leads the current. Alright, this is where it all comes together, the main event. What on earth happens when we put all these different components, the resistor, the capacitor, and the inductor, into one single circuit? So let's quickly recap the battle that's happening inside this circuit. You got the resistor, who's just chilling, not picking a side. You got the capacitor, trying to pull the current forward. And you've got the inductor, trying to pull the voltage forward. It's these competing forces that we now have to combine. So, when you throw all these different types of opposition into the mix, we give the total opposition a new name, impedance. We use the letter Z for it. It's the grand total of everything fighting against the current. Now, I know that formula might look a little scary, but don't worry. It's basically just using Pythagoras' theorem to combine the simple resistance with the winner of the tug of war between the two reactances. And all of this whole battle, it leads us to the absolute coolest phenomenon in AC circuits, something called resonance. This is where the magic happens. I want you to really picture this in your head. It's like a tug of war over the timing of the current. On one side, you have the inductor pulling and trying to make the voltage get ahead. And on the other side, you have the capacitor pulling and trying to make the current get ahead. They are in a constant fight, working in complete opposition to each other. So, what if we could rig this game? What if we could find one specific frequency where the capacitor's pull is exactly as strong as the inductor's pull? Well, that perfect sweet spot is what we call resonance. At this one unique frequency, their opposing effects on the timing just completely cancel each other out. It's a perfect tie. And here's why that is so incredibly important. This is the golden rule. When those two reactances cancel out, what's the only thing left fighting the current? Just the plain old resistor. That means the circuit's total opposition, its impedance, drops to the lowest it can possibly be. And what does Ohm's law teach us? When opposition is at a minimum, current flows at its absolute maximum. So, is this just a weird physics thing or does it matter in real life? It matters big time. This is exactly how you tune a radio. A radio is basically just an RLC circuit. When you turn that dial, what you're actually doing is changing the capacitance. By doing that, you are changing the resonant frequency of the circuit. You are literally searching for that one specific frequency where the signal from your favorite station is allowed to flow through at maximum strength, while all the other radio stations are just blocked. It's brilliant. Okay, let's bring it all home. We are going to wrap this up with the essential toolkit you need to walk into that exam hall and feel like you own this topic. Alright, here it is, your exam toolkit. Screenshot this, write it down, whatever you need to do. First, converting between peak and RMS. Second, the two formulas for capacitive and inductive reactances. Third, that big one for total impedance. And finally, the formula to calculate that one special resonant frequency. If you can master these four, you are in fantastic shape for your exams. And I'll leave you with a final question to chew on. We talked about radios, but where else in all of modern technology is it absolutely critical to select one specific frequency and ignore all the others? Think about Wi-Fi, your phone, even medical equipment. The principle of resonance is everywhere once you know to look for it. Good luck with your exams. You've got this. For more practice questions and solutions, visit examkeeper.com.